So let's wiki what is epitaxy mean. So if this is the answer from what is epitaxy? Epitaxy comes from the Greek root. It's a 希腊字三个字的Greek root epi, okay, already epi, meaning above something at top. And taxis meaning ordered manner, 规矩排列。So that means you want to put something in the ordered manner above another stuff. So it is for the epitaxy. So depositing SiO2 on the silicon substrate, is that epitaxy? Yeah, let's check with more people. Depositing SiO2 on silicon, is this epitaxy?
Yes.
Yes. How? Why?
I guess.
Okay, no, actually no. Yeah, you are all very unlucky. No, SiO2 on silicon nitride is not epitaxy. Because the SiO2 on the silicon nitride is amorphous. It doesn't have the same crystal with your silicon substrate. Because your silicon substrate is an ordered crystal. But SiO2 is not. SiO2 even is in ordered structure, we call it quartz, 石英. Its crystal is also not the same with the silicon, so it's not epitaxy. So epitaxy has an important definition that the layer deposited on your substrate or the underlayer, you need to have the same crystal symmetry with below. So it's like you cannot put, for example, you also can stack many things together. You can stack a bomb and a vegetable and meat, another bomb. We call it hamburger. But it is not epitaxy because the crystal structure between your bomb and your vegetable and your meat don't have any correlation. You are just putting things together. But epitaxy means the things you're putting up has the same crystal structure from your bottom. For example, if you're putting a Lego, you should play with Lego. Lego is some kind of epitaxy from the broader view. Because you see that you have the same crystal of the small bomb. And you need to put the crystal with the same bomb so it fits. Yeah, so the layer in the top layer and the bottom layer has the same ordered manner. Yeah, so stacking Lego is some kind of epitaxy. So this is the concept. So you have a high crystal quality of the substrate. After epitaxy, you will have a high crystal quality base, and that's very important for doing the semiconductor analysis. And in the net, while we converted this concept from to the Mandarin, we call it 累积. And I think 累积 is a very good translation because it translated what this process means by how it looks and what it means. So you split it to 累积, you have to 10, 所以你在上面堆10，然后在上面下面是堆日，上面就堆日，下面的东西要跟上面的东西是一贯的，而且要有一样的顺序，而且它们都是晶体。Nano crystal. So 累积 is a very good translation. So the elements you first you need to have a substrate. You have a substrate or template. It is already a crystal. Then you're depositing something on it, which it could be the same crystal, it could be another crystal, but anyway, the things above it need to be coherent in crystal structure from bottom to the top. So that's why I say why the SiO2 is on silicon. It's not a epitaxy. That's the reason. So okay, let's check another question. So it's easy to get bonus point. So this is the translation of in Taiwanese Mandarin. Laser, we call it laser. Yeah. This I think is a very good translation as well because they have the same sound and also give you some image about the light comes out, like this. And the epi, we call it 累积. But do you have idea what these two things called in the Mandarin? 对岸他们用语跟我们不一样。
Laser 是激光。
OK， 那累积呢？
累积我不知道。
我刚刚还写在黑板上，可能没有人看到。OK， 至少对一个。累积是什么？有没有人知道的可以举手？对岸，如果这种因为现在讲，我当然对岸的科技新闻常常跑到我这边来。好，大家都很专心看课，没有看到我刚刚在对面写什么。累积在对岸那比较外延，或者外延片。对啊，其实一样是翻译，两边的方面不一样。台湾的是真的还会想要就是要多重解释，像这个除了那个意义要有以外，还要有音要一样。然后呢，这个是形一样，就是除了那个就是形跟义都有顾到。那个应该要这两个词但我觉得其实他们翻的也不错，他们非常直接的把这个东西的物理用大白话讲出来。雷射的话是受激辐射所发出来的光。对，所以叫激光，所以那对方那边说什么这个激光盘，那个的意思就是他们是用镭射写出来的那个嘛，那我们通常就要光盘。那外延的概念是一样的，它意思就是说你今天有个晶体，你长的东西都只是在那个晶体向外延伸所产生的物理，所以叫做外延。对，有时候你看到新闻，它用的词是什么，你就可以知道它的来源是从哪里来的。如果他用到外延片，但是他用繁体字，那你就可以知道这可能是有人从中国那边找了一则那个科技新闻，然后呢翻译成中文，看都没看就直接贴出来。那如果是在台湾，就是科技教育从台湾来的，会用的词应该都是上面，那下面的词就是大家听听就好了。So why do we need epitaxy? 就是医生那边就是 deposition 那边的。Yeah, epitaxy is important because if you can do epitaxy, you can assure the things you deposit is also in crystal. So, for example, if you deposit the silver film with common EV evaporator, then because the growth rate is too fast and the temperature is not high enough, although you looks like a shiny thing and you looks it's pretty good, but if you do an AFM film, you will see it's actually a very small growth. So many programs in nanometer level. So although macroscopically it is flat, however, if you have an electron or optical wave traveling on that, it will be scattered by so many grain boundaries. However, if you do the deposition, the silver with molecular beam epitaxy, we will tell you that later. What's that later? You will get a silver film layer by layer with a very ordered manner, but you cannot grow it too fast. However, as long as you can grow a silver film like that and put something like that, it will easily give you strong plasmonic effects. So this is also, although don't have many practical use for writing paper, this is something very useful. So that will be another example of what's the difference between the common deposition and the epitaxy. And the epitaxy will also give you a high crystal quality. So although you are depositing different materials, but to electrons and the light, that will see them as the same thing. So the light will be propagating within that without additional scattering. So the light-matter interaction will also be strong. And the epitaxy with those two, we might change the composition of your alloy by growing different levels of amount. So this is something functional. Yeah, so you might give an LED with different light. That's also the better epitaxy. But however, if you can tune the composition with other methods, then probably you still do that. And the final, because the epitaxy is a very careful process. You do it by like layer 1, layer 2, layer 3. So if your process is well controlled with your flow and time, you will get your composition layer by layer by layer by layer. So you can have a very complicated structure. For example, if we just mentioned the PIN structure, the DH structure, WH structure, you have 3 layers. P-type material, I-type active region, and the N-type material, so 3 layers. But however, in the common VSO, the vertical laser, you have your cell phone. It usually has around 100 layers. Because you want to grow something called the DPR, that is a mirror and constructed layer by layer by layer by layer. And you usually need 40 layers to get a very high reflectivity. And so bottom 40 layer, top 40 layer, and probably more structure in between. And that will be a part of our courses of this course. So don't worry about that if you don't know something like that. So for example, you need a device, need 100 labels. If you don't have a tool with very strong precision and a high level automation, 自动化, it is also impossible. So epitaxy is the core technology for the modern optoelectronic technology. While we are talking about the light source, 光源, it is very important to have a good epitaxy. If you don't have the material, you are just doing your imagination. Yeah, that won't have a strong impact. So about technology, how do we achieve epitaxy? Because there are so many tools about the precision field. Like the PCVD is the tool of the precision field. EV evaporator is a tool of film deposition. Spin coater is also a way of deposition film from liquid. Yeah, but they are all not epitaxy. While we're talking about epitaxy, the number is few. Probably less than 10, probably less than 5. And in history, the most free benchmark epitaxy technology is the LPE. Liquid phase epitaxy, MBE, molecular beam epitaxy, or MOCVD or MOCVD. There are 2 names. I will give you a different. We will have a story on that. We will have time. MOCVD. This is the time schedule. At the beginning, the development is the liquid phase epitaxy. It's around the 1960s to 1970s is in the beginning while we are developing the aluminum gallium nitride T-short bipolar transistor. Yeah, in the beginning it's done by the liquid epitaxy, but it has some difficulty. If you cannot do a difficult structure, then it comes the molecular beam epitaxy. And it started with the 1970s and still popular now. But because the MBE is a very delicate procedure and the growth rate is really slow, very, very slow. So although it is good for you to do scientific research, yeah, but if you want to grow some IP to make money, probably that will be difficult. Or you need to sell your epi wafer in a very high price, then that will be difficult to compete with the epi by MOCVD. MOCVD is the latest epitaxial technology here, and although its precision is not as good as MBE, but it's not so bad. For most of probably 90% of applications, it is good enough for LED and the laser diodes. And currently, if things can be done with MOCVD, that will be the mainstream. Because you can make it a very high volume, so you can make a lot of money. So you have money to support your machine. It will be a possible positive feedback. So that will be the current scenario. And we will have a very brief introduction one by one. So what is liquid phase epitaxy? Liquid phase epitaxy, probably you actually want to do that in your elementary school. You say, what? How could I have once done LPE? Well, I'm so young. So LPE, the concept is the same. You are growing your soul crystal. I don't know, do you have a similar experience while in your elementary school 在过饱和的盐水中，你拿一个那个盐的精力泡在盐水里，然后那个精越出来越出来。这个概念就是 LP。Okay, so that means you are growing your crystal in an oversaturated melt. Because it's oversaturated, if you put a crystal in, it will grow a film on it because it's a process of precipitation. Yeah. Then the way is brutal. Consider you have a three parts of oversaturated melt. The first part A, probably a melt of gallium and arsenide. And the part B is a melt with gallium, arsenide, and indium. Yeah, and the composition is tuned at the beginning. And the layer C is another gallium arsenide. Okay, so you have the bolt and your substrate here. And you just like pull from A to B to C. So while it's in A, the melt A will depositing on the substrate A, become your first layer. Okay. Then after leaving, it's because then you deposit your second level, and then C, etc. So this is called the slide ball method. Oh, and eventually, probably think that this is too difficult. You need to have a strong body. So there's another improved way called the dipping method. Just like you're dipping your salt with your chicken. Yeah, so this is the sauce, and you put the material in and out. Okay, so probably you don't need to put so much force, but the principle is actually the same. So what's the advantage of LP? You know, LP is easy to build. So this is the first, and the concept is very simple, easy to build, and the growth rate is very fast. So if your device structure only have very few layers, probably less than 5, yeah, surely you can have so many bolts and the precision is done. But consider if you have a vessel, have 100 layers, the process will be pretty ugly. Yeah, so probably not so very. So liquid phase epitaxy is early development for the early devices with very few layers. However, the main drawback is the growth rate is too fast and difficult to control. You might, if you grow to grow, for example, 10 micron gallium arsenide, it didn't bother you only grow 9.5 micron or 10.5 micron, although the precision is bad, but that doesn't matter. Yeah, 9.5 micron in the 10 micron probably doesn't change your device behavior. However, if you're growing a quantum wave, only 3 nanometer, it is almost impossible. Yeah, people try, but this is very difficult to control your quantum wave between 3 nanometer and the 5 nanometer. Yeah, people once tried to do a very thing, and they are very proud of. Okay, you see, I deposition something like 10 nanometer film is LPE. That's what people once tried to do, but eventually it's not practical. It is only for publication. So you need if your structure need a nanometer level solution, like liquid phase epitaxy is obviously is not an option. So people try to developing another second idea called the molecular epitaxy. Molecular epitaxy, the concept is also simple, but the environment is very difficult to build. We have it is a chamber. The chamber we put something with a very high vacuum. How high? Probably from 10 power minus 9 to 10 minus and 12 is more than less than 1 billion ATM, yeah, at most billion. So actually, to build this chamber, you need for example, 10 days of pumping. You need to really pump it a very long time to get such low pumping, low pressure. And then you have some source, elemental source. For example, if gallium arsenide, probably you have a tube of pure gallium element and another tube of pure arsenic. And while you open this chamber, because the pressure is so low, the solid material also evaporates. You say because the pressure is low, you have some of the saturation pressure. That means the material is also diffusing out of the element. Alright, so while the material coming out of elements, it will, because it's also, it called diffusion because it's not, what's the difference between diffusion and diffusion? If a material comes out with not interacting with anybody else, just go the direct line, it's called diffusion. But diffusion is a series of diffusion. Diffusion is a series of diffusion. That means it comes out and probably pump to each other, and the sunlight go back and the pump again. So it's a random process. But the things still eventually goes from high concentration to low concentration. While the pressure is really low, it is called diffusion because while the atom evaporating out of the cell to your final substrate, it just works in a direct line. So how do we change the composition? For example, you have probably this is your gallium, this is your indium, and this is the arsenide. So how to change the composition of 50% indium and 50% gallium? You just do a very fast shutter. That means things are coming out, but I can cover it so the subject cannot see that. And just changing the frequency of your shutter, you can also control the flow of your element. And because the vacuum is so low, the atoms reaching your substrate has enough time to align itself into crystal structure. Just like if there's a door here and I let 100 people come in simultaneously, and they will be crowded, and the chair might be like originally probably in a good manner, but because that's too many people come in, they eventually don't sit in a good manner. However, if you just let the people come in one by one, and they come 1 people, and I ask them to do the first thing, and the second 3, 5 goes. So this procedure is slow, but that will make the coming material have enough time to align with your substrate, little by little by little. So you have to, and you can change the time of the shutter to decide how thick or how many atomic layers you have during this kind of process. So the concept is actually not difficult. It's just a simply diffusion process. The AOC is all about controlling, like how fast you need to do the shutter and how high the temperature you should do. This is just pretty technical. So the most advantage of the MPE process is the first, this is a very clean environment because there's almost nothing inside. You already pull almost everything out of the chamber, so it's definitely a clean process. And the second, because you let the atom flow in with a very slow rate, so you can get your layer with a very high precision. We did even something called the RGB monitor. To monitor your film will be half layer, one layer, half layer, one layer. It is technically can deposit half layer of atom with MBE. That's the other tools cannot do. Yeah, so you also have a very atomically sharp interface that will be totally in agreement with the theoretical design. But there's also drawback. So the drawback is also comes from its advantage. The first is ultra high vacuum is a nightmare. It's a practical nightmare. So such the high precision and the delicate working environment make it the scalability and the throughput problem. Consider if you have one substrate here, you want to double the throughput, you probably need to make the chamber twice large or 4 times large. That will make the vacuum even more difficult. So anyway, this is the one word profitability. While you're using MBE, it is very difficult to make a business to maintain your machine. Yeah, so this usually happens in the military research or scientific research. That the country will pay you money to maintain that. But for practical, it is not a good idea. So yeah, it's commonly used for research purpose. And some stuff really need this kind of level of accuracy. You don't have a choice. Yeah, you still need to do the MB structure. Yeah, so for some constant cascade laser or photonic integrated laser, it is still the MB as the major material source. And they are all very expensive. Yeah, but since you don't have any alternative, so you have to do that. Okay, then comes the third design called MOCVD. MOCVD is called it's an abbreviation of Metalorganic chemical vapor deposition. Okay, so that's a long word. So I will give you its name in Mandarin. But and there's also another name. We call the MOVPE, Metalorganic, Metalorganic vapor phase epitaxy. Yeah, so in this case, it's called the MOVPE. So what's the difference between MOVPE and MOCVD? Actually, no difference. But you can read the paper. If some paper writing in MOCVD, that means this scientist is from America, or he is educated in United States. Yeah, so I usually use the MOCVD. However, if some people use MOVP, probably he's the scientist in Europe. yeah, that's true. That's an argument between this regional use. Like European people, they think that the MOVP is the right thing to say that because it has the word epitaxy. That's the nature. You shouldn't even it up. But I don't know why US are usually saying the MOCVD. Yeah, so the case is a deposition or a epitaxy. Sure, epitaxy is a subclass of a deposition. You have so many ways to deposit a film. But if your film has the same crystal structure with your substrate, then it's called epitaxy. So epitaxy is a class of deposition. Yeah. So I think there's some commercial argument between the US company and the European company. They have a different opinion about how to code that. Yeah, this one. So the process of MOCVD is that he want to improve the problem of the ultra high vacuum. So we want to make the material or the chamber to maintain a relatively low vacuum that we can handle. For example, 10e minus 3 torr. Yeah, 10e minus 3 torr is easy to achieve. You only take a few minutes to achieve that, and it's easy to maintain. However, with such a low vacuum, you cannot let the element to evaporate under such vacuum. So how do we bring the element from source to your chamber? So it introduced something called the metal-organic chemicals. Okay, let's give you some example. I think we have okay, later familiar there. Let's take aluminum as an example. So MPE, for MPE, it is aluminum in solid under high vacuum become the aluminum in gas phase. And this requires your P to be less than minus 4. And this is the problem and the benefit of MPE. So, but however, if you only want the pressure to be in 10 minus 3, 4, even 1 atm. Yeah, 1 atm means you don't need any vacuum. Then how do we bring the aluminum? We make some chemical reaction first to make the aluminum become trimethyl aluminum. Aluminum. And the structure looks like this. It's an aluminum in the center with 3 CH3 on it. 三甲基磷. So this material has a much higher saturation vapor pressure, 它的饱和蒸汽压很高. So even under low pressure, it will evaporate from its source. So this is called the metal-organic because you are the first step is preparing some source of metal, which is isolated with organic ligands. Then those materials, this is the aluminum source, for example, TMAL source. You inject nitrogen or the hydrogen source into the source. We call it bubble. You are just giving bubble inside that. Then you have some vapor outside, and you're pushing the flow from your source to your reaction chamber. So everything could happen under a rather low pressure. So this is, and so it's called metal-organic chemical vapor phase because you are drawing the material in the phase, in the vapor phase. And while in the vapor phase, you get the substrate is have a very high temperature. So when it meets, when the CH3 meets a hot substrate, it decomposes. When it is hot, this ligand leaves. It becomes an aluminum agent on the surface. So that will be something like that. You have a metal organic flowing out into the chamber, and it meets a substrate at high temperature. Then decompose, become the atoms at the surface. Then realign, then you grow the film. That's the whole process. Simply put, for the very simple version. So this advantage is that we can still, because we are still flowing things little by little, not as much as the LPE, but much more than the molecular beam epitaxy. It is something in the middle. So the thickness control can be down to nanometer. It's difficult to control to layer by layer. but it is also as long as you manage your flow correctly, you can calculate your field by time in the second level. Yeah, for example, if you want to do LPE, you need to change. You need to cut the time to 千分之一秒. That's practically impossible. But however, you are growing your MOCVD, you can change you can control your time in probably 10 seconds, 20 seconds. That's practically possible. So that we can still do a pretty decent control of the growth speed. So with the pretty decent thickness control, you can have a delicate structure in your epitaxy. Okay, and basically it balances the good and the bad between the LPE and the MBE. It has a decent growth rate, good precision, and everything is fine for your practical conclusion. But surely there's still some difficulty. For example, it is a complicated instrument to build and maintain. So it's always a big issue that very few people in the university can really growing crystal by himself. It's very difficult because you're involving so many chemicals, so there's so many safety issues. So for nitride materials, it's almost 100% use MOCVD, but for some particular reason, MBE cannot grow a good nitride material. That's another exception. And for complicated structure, needs certain throughput and the probability. Yeah, we also use a material with the MOCVD.